as I'm having them.
Talk to me.
Yeah.
I didn't remember how to do it.
He was like,
I know. I have a review of how to do it. And I
just like so cute.
That's just a loss of alcohol.
It was like that.
What in the world were you eating?
Because you
I
could
made
have
this myself.
Yeah, that's how you
I
made
mean,
last
right.
semester.
Yeah. I was with, I don't know,
Nobody else in the world can order.
Aaron Phillips.
Oh, that's cool. Those names sound really
Every time I
good.
go,
Yeah,
yeah,
right.
I would get
My teacher, or
Yeah.
probably. I don't know. I don't think. Oh wait, Phillips?
Yes.
Yes. Yes, she's there.
And then her,
I know her like
I have two for math classes.
and
So it's like I'll be putting three.
she was on
Take calculus.
science was
yeah. They're just and same with switching. They like we'll talk about it that day. Do you want to switch for history and science? Because my co-teacher does history and I really like to switch. I know, right? It's weird. But, and they just like pick and choose. It was funny. The coach, she told us about how angry she was when her students yesterday. And she got home and started for free. She was like, maybe it wasn't them. Maybe it was me. I was like, great. I didn't even think that that was going to be an issue. Excited. I don't know. I think it's like funny. Oh, it's okay. That's such a wankster thing to get at their fair. Oh, I bet your son loved it. Did you take it?
last year we went.
Oh, cool.
It was,
Loved it.
it's just,
That's how I feel. I'm like, Monster Jam. That's so funny. No, today's actually one of my girlfriend's 21st birthday, but it's every Monday, so how fun can that be? So we're gonna bring drinks to the fair and just get hammered at the monster truck show tonight. And
is alcohol allowed?
probably not, but we're just gonna put them in cups where you can't tell.
I don't know.
I live literally like 2 blocks away. So we walked there. I used to go there, but now I'm like, I have to go 3 times.
Yeah.
Like 3 times. But like I'm going tonight. Go to monster trucks. Tomorrow I'm going for something like that. So like I have class, so nights get that one and then just set her all my stuff. What do we do? I feel like she said that thing. Oh, that's smart. You organize all your problem. And then we have chapters of the problem. So we're just going to do first last.
I'm
Did
only
you skip
up
9?
to- I'm only up to 10. I did 10.
Yeah. I think I have 10, 11, 12. And I emailed her my assignment seems. Yeah.
But I'm trying to.
Do it up so you don't
Yeah.
have to do it all
I'm
again.
such a big procrastinator.
Yeah.
So,
Didn't she say something like she emailed us something last week that we didn't do? And so then I think she said something about it this week.
was it to like watch those videos
Oh,
or something like that?
I think that maybe. Oh no, that's your thing.
Pencil
That's all
pen?
it-
I always carry extra.
I usually do, but my dog ate my
I said there is a greatest thing. So I said, wait, what does it say? There is not a greatest?
Yeah, there is no greatest.
Is the negation?
Is the question.
Oh, so then you just take
So
the
then
no
there
out.
is greatest.
And then I did it kind of weird, but it made sense. I did let n equals n, then did n greater than 2n, and then divided the 2 over until where n divided by 2 is greater than n, so like that n divided by 2 is greater than n. It makes sense once you get it, yeah. Well, it's still a rough draft.
It's just the second.
Oh, so just fill out the template?
We had to create a template. We also emailed us
See,
and said,
I need to pay
ignore
attention.
ignore the disciplinary template. Right? So, not really being part of this. So,
I guess I should do it.
we just have to.
Okay, well, I need a lot of time on Wednesday. I told you about that? He's trying to write a book that he asked me. Couple of the
Probably
2000
not right about
Right? Oh my god! And he goes to conferences literally every week. And Dunning told him, she was like, you can't be doing that.
I think we should focus on classes.
Right? And so he wants me, not Chris Thompson, the other Chris, whatever his last name is, the older, no, the younger Chris. And he wants me, Chris, and then a couple of other people, and then I think some like practical teachers, and it's all about narrative mindset. Like, there's this, and it's like this huge thing. I don't know where the main thing was. So first it was like this letter to say like I'm so excited for you to participate in the story of developing narrative. And he said, he was doing last week, and he said, I want you to have 3 worksheets to me by Wednesday. 1, 2, 3. It goes all the way to like 8. Yeah, 8 exercises. So I told him, I was like, listen, I'm very overwhelmed. I can do this because this is a lot of schoolwork, OSCA, state stuff with OSCA.
You are.
And I'm like, plus I work 6 to 7 in the morning. Like, that's not, I'm not saying right now. That's too hard.
Oh my gosh.
And he was like, oh, okay, we'll work through it together. As long as you just have another 2 weeks. This Wednesday is good stuff. Which I have the first exercise done. And how much do we want? you're good. Yes, but I think I just compensated. But I couldn't get it.
Oh wait, I clicked on it.
Yeah. No, it makes sense. Kind of. So, the lucky points, the 40 points, or just the templates, not the actual read? Yeah, you teach it to just, you just need to make your own template.
Yeah, you don't have to
Change
do
it
the
again.
disciplinary one.
Which email are you getting? It says, we will note that I added a change to the lesson plan, or to the lesson plan assignment. After talking with students, you will not be looking for a disciplinary guide template, although you can make one when instead you will customize.
No, speak to your work.
I see. That's like the most recent one I have. There's, I'll show you. You can see inside here. Like I was wanting to do the consent, or wanting to get feedback on. And the one who says he did, he specifically said he doesn't want us to focus on. So then they would have one full lesson to do. To clarify. This is what you guys can do this, but if you want to do your first class or look at your first lesson. Don't go into education. Ernest, don't go into the education.
I do not. I can't stand the thought of having to deal with these kids.
Bring some cans and put it in the pot. Yes, anyone can bring cans and put an education person.
What is this?
I think it's a bag for someone else. And my box is so cute. I feel like everyone should bring a can just because how much time I put into this box. Actually, I really didn't put that much time into it, but it looks like
Hey, let's check the attendance.
Yeah. Plus, I love painting. So
Megan.
Here.
Elsa.
Here.
Morgan.
Here.
Allison.
She'll probably be here soon.
Yeah, she'll probably come and leave.
Okay. Katie.
Here.
James. Oh, okay. Jesse. Not here, right? Leah.
Here.
Catherine.
Here.
Curtis.
Here.
John. All right. Okay, first of all, any question about homework? No? No questions? Okay.
Can we ask about 18?
Yes, number 18, the last one. Okay.
Yeah.
Yes.
Last time I did give 3 examples for the first 3 questions, but not the last one. So let's see if we can. This on. Okay. Well, the last one, I think I did ask you guys to do the first step of indirect proof. So what is the first step we always do?
Assume the opposite is true.
Yes, where we call it negation. So what is the negation of the whatever they want, the statement they want you to be proved? So they want you to prove at least one of those two numbers is less than 25. So what's the negation of that? Well, let me go ahead and write down that sentence. So at least one of the numbers is less than, I'm just going to put it this way, less than 25. So we do negation. Daniel? Neither of them?
Neither of them is less than.
Okay. So neither of the numbers is less than 25, which is correct. But is there another way to say it? To rephrase it?
Both are greater than or equal to 25.
Yes. Okay. This way, they're equivalent. Both of the numbers are greater than or equal to 25. This, if you can think of it, can you all see that are equivalent? These
Yes.
two sentences? Yes? Okay. If you can't, you can use De Morgan's law to help you to see that. For example, the numbers, we have two numbers. Let me just call them, let's say what we call them number 1 and number 2. Well, we can just call them A and B. So let's call these numbers A and B. So when you say neither of the numbers is less than 25, so it's kind of like saying A is not less than 25 and B is not than 25, right? Okay. Neither of them, which means A is not less than 25, B is not less than 25. So, which is A is not less than 25 when you rewrite it. It's like A is what? Greater than or equal to 25, and B is greater than or equal to 25. I guess we don't really have to use the Morgan's law then. Okay. So you pretty much just rewrite it this way. Okay. All right. So this is the one you can use to get a contradiction. Okay. So by the assumption, we assume the first, both numbers are greater than 25. You can use the letters, say A and B, X and Y, whatever you want to use. So you would get conclusions like A is greater than 20 or equal to 25, B is greater than or equal to 25. The next thing you want to do is to find a contradiction. Usually, where does the contradiction come from? Most of the time, it's contrary to what's given. Sometimes it's not. Sometimes it's contrary to some fact everybody knows. But in this case, it's going to contrary to this statement given in the problem, the condition. Because they tell us the sum of these two numbers is less than 25, which means A plus B should be what? A plus B, rewrite it. If I call these two numbers A and B. So A, the sum means addition. So the A plus B should be less than 50, right? But look at what we have. A is bigger than or equal to 25. B is greater than or equal to 25. What do you think the sum will be of these two numbers? So when you have those, A plus B is going to be whatever. That should be contrary to the condition given. Okay? So they tell us when you add them, you should get a number less than 50. But by the assumption, both numbers are greater than 25. When you equal to 25, at least 25. When you add them, you're going to get a contradiction here. Okay? All right. Is that clear?
Yeah.
Okay. All right. So that's the last part. Any other question? Okay, if not, we're going to move on to 3.7. Still going to continue indirect proof. But the problems we're going to do today will be, the first one, I think I already gave you an example last time. First homework question, like prove that for all integers a, if a cubed is even, then a is even. The example I did last time is squared. So we can go over that example one more time to help you do this. I guess I forgot to put my page. Okay, so we can review that example. So what I did in class last Wednesday, we did if a squared is even, then a is even. Okay, a is an integer, of course. So how do you remember how we did this problem? How do we prove if the square of a number is even, then number has to be even? What do we do? Can we prove it directly? Can we?
No.
No. Okay. I do have that slide here with me. So if you try to, okay, this is the other session. Maybe I just put on the. So if you want to do the way we did before, say, okay, if it's even, that means it's 2k. Then you're going to have a squared equals 2k. Well, how do you show a is even then? In order to get a from square of a, what operation do we have to do? How do we get a from a squared?
Square root it?
Yes, you have to take the square root. But if you take square root, you're going to get the square root of a squared is a, but square root of 2k. Can we tell whether this number is even or odd without knowing what k is?
No.
No, you can't, right? Okay, so it really depends on what k is. Sometimes you could get irrational numbers. But I mean, if it's a squared, of course you shouldn't. But just by looking at square root of 2k, there are so many possibilities. If k is 2, you're gonna get. If k is 1, you're gonna get 2 times square root of 2 times 1, which is square root of 2. It's even irrational. Of course, you cannot be even. But if k is 2, yes, you will get even number. So we don't know what k is, so you won't be able to do anything about it. So that's why you cannot do it directly anymore. But the one we proved before, if a is even, try to prove the square is even, direct proof will work because 2k is the even number when you square it. You're not going to get square root. You're going to get still whole numbers, integers, and which you can factor out the 2. So that's the difference. Let me rewrite this so you can compare. So one question is, you know a is even, and you want to prove a squared is even. In that case, yes, you can use direct proof. But if you know a squared is even and try to prove a is even, you cannot prove it directly. You have to use indirect proof. Because in order to get a squared from a, you can square it. So when you have 2k and you square 2k, you get 4k squared. There's no radicals. You can show this is even number. 4k squared is even. But if you have a squared is even, in order to get a from a squared, you have to take square root, which is impossible to tell whether square root of 2k is even or odd. Okay, so that's why we have to take indirect proof. So we assume, by way of contradiction, we suppose a is not even, which means a is odd. Because there are only 2 kinds of numbers, either even or odd. If it's not even, then it has to be odd. If a is odd, we can let this number be 2k plus 1. That's how we describe any odd number. Okay, we cannot pick a special odd number because we don't know which odd number the A is. But 2k plus 1 can represent all the odd integers. And now the next step is to get a contradiction. How do we get a contradiction? What do we do? So usually, most of the time, the contradiction you get is going to be whatever the conclusion comes out from your assumption. So A is 2k plus 1. You're going to be able to get some kind of conclusion. Whatever that conclusion is, usually it contradicts to the condition given. So they tell us A squared is even. So we're going to try to see whether A squared is even. If A is odd, you can square 2k plus 1. And we end up with 4k squared plus 4k plus 1. And by looking at it, we know it's odd. Well, to prove it, we factor 2 out of the first 2 terms. And that's an even number because 2 times the integer. It's even plus 1, that's odd. So here's the contradiction. The problem tells us A squared is even. That's like a fact. That's like evidence you collected. So A squared is even. But we found out A squared is odd. Same number, A squared, has to be either even or odd. It cannot be even and odd at the same time. So that's the contradiction right there. I did last time. I already had this. So if you took notes last time, I have the detailed proof there. So over here, what the contradiction is, you can write it down. Contrary to the condition that A squared is even. I just put the symbol here means that odd and even are contrary to each other. But it is kind of obvious, but probably it's the first time you write in proof, you should write it down exactly what contradiction is. The contradiction is, or if A is odd, the A squared is odd, which is contrary to the condition that A squared is even. Okay, so that's the problem I did prove last time, but I just want to go over this one more time here. Now next we're going to look at one of the classical theorems in number theory. I think most of you are going to take number theory, which you will probably look at those proofs again in that class. So the first one is 3.7, 2 classical theorems in number theory. Classical theorems. So these are also, I think everybody knows square root of 3 is irrational, but we never asked to prove why they're irrational. We just assume, okay, it is irrational. It's a radical number, it's irrational. But here we're going to learn to prove it. So you know for sure, okay, yes, it is irrational. The first thing, the one I am going to do is to prove square root of 2 is irrational. So maybe you can follow this example to do square root of 3 or square root of 5. Any like square root of a number is irrational of square root 2. So square root 2 is irrational. Okay, we know, I explained this last Wednesday. You cannot prove it directly. In the homework or on the practice exam or on the first exam, we did have a question that, let's take a quick look over there. If you want to show something is rational, you can, like the last, number 14. How do we prove this expression is rational? Well, all you have to do is to plug it in. So R is rational, which means R is A over B. And you plug it in here and you can use algebra, do algebra work, and you get a single fraction, something over something, integer over integer. But, so that shows something is rational. Most of the time, if they ask you to prove something, a number is rational, expression is rational, you can do direct proof. But if they want you to prove something is irrational, it's almost impossible to prove it directly, because that means you will have to show irrational means. So rational means it's an integer over integer. That's rational. It's easy to show. But irrational means it's not an integer over integer. Well, how do you show a number is not an integer over integer? In other words, instead of saying integer over integer, let's just call this a fraction. It's easier for us to say. So it's kind of like you have to prove this number is not a fraction. So how do you show square root of 2 is not a fraction? Wait, can you say it a little louder?
Break it down using algebra. It doesn't equal in square root of
Okay, so you're trying to do indirect proof, is that right? Okay, yeah, so yeah, we have to do indirect proof. But before we do that, I want you to, I want to make sure you understand why we cannot do it like before. Prove it directly. So, because when you try to show something is irrational, you will have to show it's not a fraction. So how do you show square root of 2 is not a fraction directly? I mean, okay, yes, you have to show it indirectly. If you want to show it directly, well, you have to take every single fraction we have, say 1/2 or 4/3, to check, okay, well, they're not equal. And then pick another fraction, say 5/4. They're not equal. And pick another fraction, they're not equal. So you get to check every single fraction and show none of the fractions we have is equal to square root 2, right? But can we do that? To check every single fraction and to check the values, they're not equal to square root 2? We can't. So that's why we have to do indirect proof. So the first step of indirect proof is always what? What do we assume?
Negation.
Yes. To do the negation. So what's the negation of this statement?
square root of 2 is rational.
Yes, square root 2 is rational. Okay, and what conclusion comes from that? If I tell you square root 2 is rational, how do you describe a square root 2? Yes, by definition of a rational number, it's integer over integer. And we can use A over B. A and B are both integers. But we do want to, usually that's what we did before. So if you know something is rational, like if they tell you, say R is rational, you just let A be R equal to A over B. But over here, we do want to add one more condition here. How do I know this? Because how do I know we should add this condition? Because we already know the proof. But otherwise, you wouldn't know this from the very beginning. Because you try to find a contradiction, which you later in the process you will realize, okay, we have to. The condition will be something, and so the condition we're going to add is such that the greatest common divisor of A and B is equal to 1. Greatest common divisor of A and B is equal to 1. So what does this mean? Because when we have fractions, let's say 4 over 6, that's also fraction, integer over integer. But we can reduce this to get 2 over 3. So when you have cases like that, okay, doesn't matter which one we take. The square root 2 equal to, do I take this form, simplified form or not simplified form? So we want to pick whenever you have, it's equal to, say, square root 2 is equal to 4 over 6 or 6 over 4. I'm always going to reduce it to get a reduced form. So this A and this B, they will not have anything in common. So you won't end up with like 4 over 6. They have something in common, okay? So, and why is this important? Later you're going to see that contradiction is this. So we are assuming when I pick this A and B, I make sure A and B are relatively prime, which means they don't have anything common factor. But later I'm going to show they actually have something in common. They have a 2 in common. That would be a contradiction. Because if you pick A and B such that they don't have anything in common, then later you found out A and this B do have something in common. That's a contradiction, right? Okay, so this is what we're going to do. How do we found something in common for A and B to try to contradict that? So we're going to square both sides. And usually when you have a square root in there, you cannot really discuss anything. So you're going to square both sides to get rid of that square root. Square root and square, and sort of like they cancel each other. They are inverse functions. So we get a square over b square on the right. And with the fractions in there, usually it's not very easy to see the properties. So we're also going to get rid of the bottom. By algebra, we multiply b squared on both sides. We multiply the left-hand side by b squared. And right-hand side by b squared. B squared cancels b squared. You get a squared on the right. And the left-hand side, we got 2b squared. Okay, so no radicals, no fractions. By looking at this expression, what conclusion can you get? By looking at this expression, 2 times b squared. And don't forget, b is an integer. If b is an integer, then b squared has to be an integer. So 2 times the integer. Does that sound familiar? When you have 2 times the integer, what is that number?
Even.
It's even, right? Okay. So when I look at this, what is even? Be more specific. What is even? Huh? A squared, right? Okay. Because we can tell 2b squared is even, but a squared is the same as 2b squared. So you can say this is by the definition of the, the definition of even number. You can say then a squared is even. So is everybody clear why a squared is even?
Yes.
Okay. Yeah, everything you write down follows from a definition or a property we proved before. So this comes from the definition of even number. The definition of even number says if you can factor 2 out of that number, well, if you can write that number as 2 times the integer, then it's even. If you look at a square is equal to 2 times the integer. That's why, well, I think it's very obvious. If you don't want to put a reason there, explanation there, that's fine. If you do want to put an explanation, it would be by the definition of even number. Okay. So a squared is even. Well, don't forget the property I just proved. The problem we just proved. What did we just prove? If a squared is even, then what? The base a is also even. So this is, since I just proved it, you can use it here. So you don't have to prove it again. So a is even. Well, I can put a proved in the previous problem. In case you forget, say why a is even, proved in the previous example. So when you do the homework, you do have to show that. If you have something like that, I think you will get a cubed is not really even. I think I can explain that in a second to help you do that question, because it's not exactly the same. It's a little different. Okay, so we got a squared. A is even. Now, if a is even, I can describe a, because when I picked this fraction, a over b, I only know a, b are integers. We don't know whether they are even or odd. But after I square both sides and get rid of the fractions, I found out a actually is even. So if a is even, I can let a be 2k. A is integer. And now I'm going to plug this back into that equation. 2b squared equals a squared. So replace that a there with 2k. The left-hand side, we keep it. 2b squared equals a is 2k squared. And simplify the right-hand side. We have 4k squared. Left-hand side is still 2b squared. Now, simplify both sides. I can divide both sides by 2. we try to simplify as much as possible. We end up with b squared equals 2k squared. Now, look at this equation. What conclusion can you draw from this equation? Very similar to the previous one. B squared is even, right? Because b squared is equal to 2 times the integer. Then b squared is even. Again, it's by the definition of even number. And if b squared is even, what about b? B is also even. Why? Because we just proved it. If the square of any number is even, then that number itself is even. Right? Okay, so the same reason. Okay, so now let's take a look at the two conclusions we got. A is even. B is even. We got two even numbers, A and B. What do you think the two even numbers, what numbers do they have in common? A common factor they have? 2, right? They at least have 2, maybe 4 or 6 or other numbers, but at least they can have a 2 in common. So based on these two, A is even, B is even. I guess I'll say, therefore, A and B have a common factor 2. Common factor 2. Well, don't forget when we picked that fraction A over B, go back to the very beginning of our assumption. When we picked the A over B, we say let square root 2 be equal to A over B, since square root 2 is a fraction, right? Rational means a fraction. It's A integer over integer. I made sure this A and B, they are relatively prime. Well, you can say they should not have anything in common except 1. But we found out they have something in common too, which is a contradiction, right? So right here you can say contrary to our assumption, contrary to the assumption that the greatest common divisor of these two should be 1. That greatest common divisor of A and B is equal to 1. So the contradiction tells us our assumption is false, which means square root 2 cannot be, yes, hence square root 2 is irrational. So go back to look at the main idea of this proof. So we want to prove the square root of 2 is irrational, but we don't prove it directly. We assume it is rational. So because if it's rational, I can always write it as a fraction. Once I write square root 2 as a fraction, I found out I got two conclusions. A is even, B is even, which gives me another conclusion. A and B have a common factor 2. So this is the one we need to give us the contradiction. So where does this conclusion come from? A and B have a common factor. It comes from our assumption that square root 2 is A over B, right? See, everything, how did I get A is even? Because I take this equation, I square both sides, I multiply both sides by B squared. I got this equation that tells me A squared is even, which tells me A is even. So that A is even comes from this equation. And then I let A be 2K. I plug back into that equation again. I found out B squared is even, which tells me B is even. So both conclusions, these two conclusions, come from our assumption that square root 2 is a fraction, is A over B. But if square root 2 is a fraction A over B, you are going to get A and B have a common factor, which is contrary to the assumption that they should have a common factor 2. Okay, that tells us, well, it's impossible. So square root 2 has to be irrational. It cannot be rational. Because if it is rational, it's going to generate contradictions. Sort of like if you assume something is true, you found out you are at two different places, like the crime scene case we talked about. So if you are the killer, you're going to have to be at the crime scene and you are in the classroom. So that's a contradiction. Or something like the conclusion follows the assumption. Let's say you assume square root 2 is rational. If you end up with something like I am 40 and I am not 40, so that would be a contradiction. So which means that cannot be true. Okay, so that's the first classical theorem in number theory. I do want to say a few words about this step right here, because when you do the homework question to prove square root of 3 instead of square root 2 is rational, or even like square root of 5, square root of 7, you can do those problems similarly. But this one is a little, you have more explanation than what I have in the example. So what I want to explain is right here. So pretty much you can follow the same thing over here, but instead of having a 2, you have a 3. So you're going to get a 3b squared equals a squared. So that's the place you have to pay attention here. So you end up with something like that. So when I have 2, I can say a squared is even. If you have 3, can you say a squared is even? No. Okay, that's not the definition of even number. Even number, you have to have 2 times integer. If you have 3 times integer, you cannot say anything. Some students in the past, they said, okay, then a squared is odd. Well, not necessarily odd, because I can have 3 times 6. That's 18, which is also even. So when you have 3 times something, it won't tell you whether a squared is even or odd. We don't know that. Okay, so what should we do then? Well, so before you prove this problem, you need to do another problem very similar to what I did in this question. Okay, so before you use this, you're going to try to prove if, by looking at this, you cannot say a squared is even or odd, but you can say a squared is what? 3 times the integer. What does it mean? A squared is divisible by 3, right? Okay, or in other words, a squared is a multiple of 3, whatever you like to say. So here is something you got to prove before you do this problem. You will say, prove if a squared is divisible by 3, or you can say a multiple of 3. Prove that then a is divisible by 3. Divisible by 3. Or you can say a multiple of 3. How do we prove this one? Similar to the one I did. If a squared is even, then a is even. So you got to do indirect proof. Let's see if it's okay. All right. So I think I can add it to this week's homework. It's not in the book, but you do have to use this. So think about how we prove this. How do we prove if a squared is a multiple of 3, then a is a multiple of 3? Again, it's going to be similar to this. To a squared is even. Because think about it, even. What does even mean? Even means a squared is divisible by what? By 2, right? Then a is divisible by 2. Or you can say, if a squared is a multiple of 2, then a is a multiple of 2, right? So technically, it's the same type of question. I just changed the 2 to a 3. Okay, so how do we prove this? In a similar way, so what we did here is indirect proof, so we need also to do indirect proof here. So what do we assume? A is not divisible by 3 or not a multiple of 3. If a is not a multiple of 3, what kind of number is that? How do you describe it? Okay, so a while ago when we talked about proof by cases, we learned to divide the number of integers into different categories, right? So you can divide it into even or odd. But even odd, in fact, means divisible by 2, or a multiple of 2. A multiple of 2, and a multiple of 2 plus 1, or odd number. Plus 1. Okay, so that's why when I did this question, if a squared is even, which means a is divisible by 2, then a is divisible by 2. But this is pretty much like assuming if a is not divisible by 2, if it's not divisible by 2, then it has to be divisible of a multiple of 2 plus 1, so which is 2k plus 1. The same as odd. But now we have, what do we have? We're saying a is not a multiple of 3. So if it's not a multiple of 3, what kind of numbers will be that? Have 3 categories, if you remember. How do we divide numbers? By using the remainder, integers, into 3 categories. Remember that? How do we divide the integers into 3 categories? Huh? By the remainder, yes. By the remainder, so what would be those 3 categories? 0, 1, 2. And if any integer divided by 3, you get remainder 0. What kind of integer is that? How do you describe it? Divisible by 3, right? Okay, so how do you describe a number divisible by 3?
3k.
Yes. If the remainder is 1, how do you describe it? 3k plus 1. And then 3k plus 2, right? Okay, so it's the same way. And this category is a multiple of 3. Instead of a multiple of 2, you have a multiple of 3. Instead of a multiple of 2 plus 1, we have a multiple of 3 plus 1. And you also have an extra category, multiple of 3 plus 2. See that? Okay, so now go back to the question. We assume A is BWOC. You're going to assume A is not a multiple of 3, which means A is not going to be this category. So what possibilities are there for A? What are the possibilities there for A? 3k plus 1 or 3k plus 2. So you're going to do 2 cases, okay? And for case 1, so if A is 3k plus 1, you're going to try to get some kind of contradiction. If A is 3k plus 2, you can get another contradiction. So both cases are impossible, which means A has to be a multiple of 3 or divisible by 3. So how do you get a contradiction? It would be the same way like I did. So for me, I only have 2 categories. If it's not even, then it's odd. So it has to be 3k plus 1. I plug it in there. I do a squared. I found out it is odd, contrary to even. So the same thing here. We're saying A is not a multiple of 3. So after you do that and do the square, okay, so you should you're not going to get a multiple of 3 either. But you should get another multiple of 3. But the problem tells us A squared is a multiple of 3. So you get a contradiction. So for both cases, you're going to be able to get the same contradiction. Okay, so the first thing you want to do is to prove this. If you want to write this down, prove if A squared is divisible by 3, then A is divisible by 3. Or you can call it a multiple. Okay. Following my first example. After you prove that, you can go back right here. So if A squared is a multiple of 3, by looking at this, what's A squared? 3 times the integer, which means A squared is divisible by 3, right? If A squared is divisible by 3, using what you just proved, A is divisible by 3, right? Okay. If the square is a multiple of 3, then the number is divisible by 3. So you do have to prove this before you do the problem. Square root of 3 is irrational. Okay. And I was trying to see if this problem is in the textbook exercises, but I don't think it is. So I would just ask you, I would just add this question in homework, and you can prove this one first and use it when you do the other second homework question. Okay, so like I said, in the homework, I didn't have that question for now, but you can, for what, 16. Okay. So, but I'm going to add a question in here right before number 16C. It's because you're going to have to use this to do number 16C. Okay. All right, so that's the first type of question, to prove square root of number is irrational. All of the questions can be done almost the same way. Now next we're going to do the second classical theorem. I didn't really give you a homework assignment for that. Let's see. Well, I probably will add a question to that. Okay. All right. So I'm going to modify this document and add another problem, number 20. I think it's number 28. So you can follow the example, my example to do number 28. So the second classical theory is called infinitude of the primes. We want to prove the set of prime numbers is infinite. Okay. Now, first of all, what's the definition of a prime number? Yes. The first way you said is also correct. Only divisible. A prime number is only divisible by 1 and itself. Well, you can say the only factors you have is 1 and itself. Yes, both are correct. Okay. Let me write down the definition somewhere, because later when we do the proof, we do use that. The definition of a prime number. A prime number. In number theory, that's also another theory you're going to do in that class. And the definition of prime number is also given in that class. So a prime number is a number, I guess, integer greater than 1. So notice that when we talk about prime numbers, we're not going to talk about 1. So when you have 1 and ask you, is 1 prime or not prime? Okay, so 1 is not prime or not composite. So is an integer greater than 1. When we talk about prime numbers or non-prime numbers, we start with 1. Start with 2. Is an integer greater than 1 that is, which way do I use? Only divisible, or that only has factors 1 and itself. You can also say only divisible by 1 and itself. Okay, so now so think about some prime numbers, like first few prime numbers. Can you list the first few prime numbers? 2, 3, 5, 7, 11, 13, 17 also. Okay, right? 17, 19, 23. Yeah, you can continue. Is there an end? Is there a last prime number? No. There are infinitely many prime numbers. You can always continue to find the next prime number. But how do you know? Because if you want to prove directly, you have to keep listing all the prime numbers, which is impossible to do. You cannot continue to do this forever. So we have to take indirect proof again. All right, so what do we assume then, if we do indirect proof? Not infinite, which means what? Finite, right? In other words, I'm just going to say, assume there are finitely many prime numbers. Assume that there are, you can say the set of prime numbers is finite if you want to do that. That's the same thing. There are finitely many prime numbers. If there are finitely many prime numbers, then I can list all of them. Is that right? If you have infinite many prime numbers, you cannot continue to. We listed the first few, 2, 3, 5, 7, and so on. You cannot list all of them because they're infinite many. We cannot. Even if you spend your entire life trying to list, you cannot finish it, right? Cannot finish the list because they're infinite many. But if there are finitely many, then you can. Then it means there is an end. There's a last one, right? So you can list all of them. So that's what we're going to do. We're going to list all the prime numbers in the ascending order. So then all the prime numbers can be listed. Say in ascending order. Okay, P1. Well, what's P1? The first prime number is, this P1 means what number? What is the first prime? 2, okay. You can put it equals 2 there. That's what textbook did, but you don't have to. P2 is the second prime number, which is 3. And P3 is the first prime number, that's 5, and P4, so on. Because we cannot really, actually, even if they're finitely number, maybe if there are 1 million of them, and it's going to be harder for us to write down 1 million numbers. So we're just going to continue this and write down, we use Pn, P sub n, subscript n, to represent this is the last prime number we have. Okay, the last prime number. P1 means the first prime number, and then you have second prime number, third, and so on. Although we can write down the first few, 2, 3, 5, 7, 11, but we cannot list all of them. Even if they are, we can write them in the list, and we can write down the last one, but we just don't know what the last one is. And we don't care. We just know there is a last one, but we don't really need to know what the last one is. Okay, so our goal is to find a contradiction. Whenever you do indirect proof, there needs to be a contradiction. Well, there's not really anything given here, right? So I said, when you try to find a contradiction, that's always like, whatever conclusion you get based on your assumption is always contrary to the condition given. For example, in the homework, last homework, if they tell you the sum of two real numbers is less than 50, you probably will get the sum of two real numbers is greater than or equal to 50. That's a contradiction. So if they tell you, let's say x is rational, your contradiction probably is x is rational. So they're contrary to each other. So usually it's contrary to something given. But in this case, there's nothing given. Similarly, in previous example, we want to prove square root 2 is irrational. There's nothing given. We don't know anything. There's no condition. So we created this condition that greatest common divisor of a and b is equal to 1. So we get a contradiction here. The same thing here. What is the contradiction we're going to get? We are saying this list right here, that includes all the prime numbers we have. So that means you cannot find any other prime numbers. Okay, so because we listed all the prime numbers here. All the prime numbers are listed in here. P1 is the first one, Pn is the last one. So you should not be able to find any other prime number, right? But we're going to construct another prime number, which is not even in here, and that would be a contradiction, right? So it's kind of like you're saying, okay, all the books I have, all the money I have is here. But then I found some money in your pocket. That's a contradiction to what you said, right? Okay, so the same thing. We are saying all the prime numbers are here. If I found another prime number not here, that is a contradiction. Okay, so How we found another prime number which is not here? So we create another number by, this is how we create a number. We take all the prime numbers we have, multiply them. So think about it. Take all these numbers, 2 times 3 times 5 times 7 times 11 times 13 times 17 times 19 times 23, all the way down to the last prime number, whatever that is. What are you going to get? You get a huge number, right? Okay. Well, we just don't know what that number is, but you get a huge number. So, do you think that number we create, and also we're going to add 1 to it. So this is the number we're going to create. Let n be P1 times P2 times P3 dot 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 all the way to the last number and plus 1. Now take a look at this number n. This number is going to be huge. Why? Because you're doing multiplication. You're multiplying 2 times 3. You don't have to write this down, but I'm trying to give you a better view of what this number will look like. So you're taking the first prime number, 2 times the second prime number 3 times 5, and times next is 7 and 11, 13. Even with the first 6 prime numbers, you're going to get a huge number, right? Not to mention you're going to continue to do this forever until the last prime number. And after that, you're going to add 1 to that number. So although this looks like a long algebraic expression, you need to know this is just a number. A very, very big number. Okay, we don't know what the number is because we don't know what the last prime number is. Although in fact that last prime number does not exist. Temporarily, we are assuming there is a last one. So we can create this huge number. And first of all, we need to recognize this number we created, this whole thing, okay? Don't look at any one of it. This whole number n. Could this be any of the numbers we have here? P1, P2, P3, all the way to Pn. Could it be one of the numbers? No. Why not? If you multiply all of these numbers, you're going to get a huge number. Definitely going to be bigger than any of the numbers here, right? Does that make sense? Okay. Is everybody clear about that? Okay. So think about it. Even if you take those numbers you multiply, say take the first few prime numbers, you're going to get a huge number. It's going to definitely be bigger than 2, bigger than 3, bigger than 5, bigger than 7, bigger than 11, bigger than 13, bigger than 17, bigger than 19, right? So similarly, if you multiply all of them, the number you're going to get is going to be bigger than P1, bigger than P2, bigger than P3, bigger than any of the prime numbers we have, and bigger than the last prime number Pn. And plus 1, it's even bigger. So first of all, we recognize that this number we created, n, is not any of those numbers we have. Say n is not P1, P2, P3, dot dot dot, and n. Okay, so the next thing I want to prove is, I want to prove this number is prime. If I can prove this number is prime, I get a contradiction. What is the contradiction? So here's the question, and that's something we're going to do next. Is this number prime? I can prove this number is prime. And if I can prove this number is prime, do you know what a contradiction is? Yes, that's right. Remember what we assumed? We assumed all the prime numbers are already here. So if I draw a circle to represent, okay, so I put all the prime numbers in this pool, P1, P2, P3, all of them until all the way to the last one. But now I found another number n, which is not here, and it's also prime. That is a contradiction, right? Because we assumed all the prime numbers here, and we found another prime number which is not here. Similarly to the one you say. If you say, okay, I put all my money on the table, so that's all my money. But then I search your pocket, I found $1, and that's contrary to what you said. Okay, you said all your money is here, how can you find another dollar? So the same way, you say all the prime numbers are here, how can you find another prime number that's not even in there? Okay, so this is the contradiction. So all it's left, everything is left to do this. So how do I prove this is a prime number? So we're gonna use that part. It's kind of like it's another indirect proof. Okay, how do we prove this is a prime number? So this is what we do. Go by the definition. What is the definition of prime number again? Only divisible by 1 and itself, right? Okay. So of course, any number is divisible by 1 itself. But I need to show, in the other words, you need to show no other number will go into n. Is that right? Does that make sense? Okay, how do you show this number is prime? So I can write this down to show, so you can see what I'm trying to do next. To show n is prime, it suffices to show none of the prime numbers divides this number. So it suffices to show P1 does not divide n, P2 does not divide n, and P3 does not divide n, and Pn does not divide n. Okay. So you want to show none of the numbers go into this number. But if you can show all the prime numbers don't go in there, that number is prime. Okay, you don't have to say, if 2 doesn't go in there, you I have to check 4 or 6 or 8. Because if 2 doesn't go into a number, 4 is not going to go in there, right? Okay? Because if a number is a multiple of 4, then it's a multiple of 2. So that's why we only need to check. We don't have to check every single number. You only need to check all the prime numbers we have. None of the prime numbers is divides n. So it looks like we have to prove a lot of things. But you only need to prove one of them. Because every other proof is exactly the same as that. So I'm just going to prove the first one. And I can say the others can be done in the same way. Okay. So let's say, so I'm going to prove P1. So next I'm going to prove P1 does not go in, does not divide n. Using indirect proof. And so BWOC, suppose what? I want to show P1 does not divide n, but I'm going to assume P1 what? Divides n, right? So negation. If P1 divides n, let's look at the expression here. The expression we have is right here. That's n. N equals P1, P2. Okay. So P1 is going to divide. Then P1 divides. What I'm going to do is this. I take this equation and move. I'm going to move this to the left. This whole thing, move it to the left. I'm going to get an n minus P1, P2, P3 times all the way to Pn. Okay, so how do I know this? Because I want to move this to the left-hand side by subtraction. So I get an n minus P1, P2, P3 times all the way to Pn. I keep that 1 there. I don't want to move 1. I'm just going to move this whole thing to the left. So that's what we end up with. And does anybody know why P1 goes into the subtraction of this? That's a homework question you did before. Okay, so I'm going to show you right here. Under section 3.3, there's a homework question number 16 right there. It says if you have, in fact, there should be 3 integers, A, B, C. When you have 3 integers, A, B, C. If A goes into B and A goes into C, then what? A divides the difference of those 2 numbers. Okay, if A goes into this number B and another number C, then A goes into the difference of them. So go back to look at our case here. Now look, A, you can think of this as our A, P1 as A, N as B, this whole thing as our C. So look, P1 goes into this number B, N. P1 also goes into this product. Can someone explain why P1 goes into the product?
Because it makes up part of it.
Yes, that's right. Very good. It's part of it, right? Is that Curtis, right?
Yes.
Okay, yeah. So we're both Curtis and James said something similar. So why does I'm going to add a sentence here because why? Because P1 divides N, right? And P1 divides P1 times P2 times P3 times Pn. So P1 times Pn, where does it come from? That's our assumption. We assume P1 goes into N. But why does P1 go into the product? That's what James and Curtis said. Because P1 is part of it. If P1 is part of it, of course P1 goes in there. Just like 2 divides what? 2 divides 2 times 7, right? 2 divides 2 times any number. So this is obvious. And use the problem we proved in the homework. If P1 divides one number and another number, P1 divides this number, P1 divides that number, then P1 should divide the difference of these two, right? Okay, so you don't have to prove why. You can just write this down. P1 will go divide the difference of them because we proved it in our homework. And don't forget, what is N minus P1 times P2 times P3 times Pn? Go back to our number. See, N equals this. If I move P1, P2, P3, Pn to the left, what is on the right side? 1. So N, that tells us N minus P1, P2, P3, Pn equals 1. Okay, so this part right here, it's pretty much 1. So P1 divides the difference of these two numbers, but the difference of these two numbers equals 1. So look at this. Can you tell what the contradiction is? I'm going to rewrite that. So P1 divides 1. What is P1? The first prime number, which is 2. We'll go back to our assumption here. What's P1? P1 is the first prime number. That is 2. And what is the contradiction? Can you see what the contradiction is now?
2 doesn't divide 1.
That's right. We proved that 2 divides 1, or in other words, 2 goes into 1. But that's a contradiction. 2 doesn't go into 1, right? That's impossible. Only 1 goes into 1. Any other number won't go into 1. So here's a contradiction. It's pretty obvious. If you don't want to say what the contradiction is, you can just say a contradiction. If you want to say it, it would be like contrary to the fact that 2 does not go into 1. Okay, that's I think it should be obvious right here. Okay, so we're done proving why P1 doesn't go into N, because if P1 goes into N, you end up with this conclusion. P1 goes into 1, that's a contradiction. Impossible. 2 does not go into 1. So similarly, you can prove P2 doesn't go into N. But how do we prove P2 doesn't go into N? All you have to do is change P1 to P2, P2, and P2, and P2, P2. You get the same conclusion because P2, if P2 goes into N, and P2 also is part of this product. P2 is in there. So P2 should go into the difference. And the difference is equal to 1. So it tells us P2 goes into 1. And it's also contradiction because P2 is 3. The second prime number is 3. So similarly, you can prove P3 is not, divisible, does not divide N. But you don't have to show me all that. I did that to show you why the other ones can be proved similarly. All you have to do is to put down a sentence, say, similarly we can prove, and this is accepted when you write down the proofs because they are exactly the same except by replacing P1 with a different symbol, P2 or P3 or Pn. So similarly we can prove P2 doesn't go into N, P3 doesn't go into N, and P4 and all the way to the last one, Pn doesn't go into N. So if none of the prime numbers go into a number, that tells us then, therefore, Pn is prime. Okay, that's the definition of prime number. If you cannot find anything except y itself, y and n in this case. So I checked all the prime numbers. P1 doesn't go in there. P2 doesn't go in there. P3 doesn't go in there. P4, and none of the prime numbers go in there. That means n has to be prime. Okay, I can give you a particular number. Let's say, how do you prove, for example, 29 is prime? How do you check if 29 is prime? You check every prime number. Does 2 go in here? 2 doesn't go in there, right? Does 3 go in there? No. Do I need to check whether 4 goes in there? No, because if 2 doesn't go in there, 4 is not going to go in there, okay? So next, you check next prime number. You say 5 doesn't go in there. And then you check 7 doesn't go in there. And you check, you don't have to check 8, because if 2 doesn't go in there, 8 is not going in there. Similarly, next 11 doesn't go in there, 13 doesn't go in there, and 15, 17 doesn't go in there. So you check every single prime number we have. None of the prime numbers go into 29, which means 29 has to be prime, right? Okay, the same way. That's why we did exactly the same way. Instead of having a particular number 29, I just have an expression for the number n. It's this expression. So think of this whole thing as 29. How do I show this is prime? I just check. I check every single prime number. Like 2 doesn't go in there, 3 doesn't go in there, 5 doesn't go in there, 7 doesn't go in there, 11 doesn't go in there. Every single prime number doesn't go in there, which makes this number a prime number, right? Exactly the same idea as you're trying to show why 29 is prime, because none of the prime numbers go in there. Okay, all right. And so now we're done. Where we have a contradiction now. We have a number n, which is none of those prime numbers we have, and which is bigger than all of these prime numbers, and which is also prime. So that's a contradiction. So I can add the contradiction here. Contrary to the assumption that all the prime numbers are P1, P2, P1, P2, Pn. Okay, so then we proved that there should be infinite many prime numbers. Because if there are finitely many prime numbers, I can list all of them. And after I list all the prime numbers, I found another prime number, which is n. So that's a contradiction, okay? So pretty much it says, if you have all these prime numbers, I can always create another bigger prime number, right? Okay, so that means there's always more there. Okay, any question? These are two classical theorems in using indirect proof in number theory, in discrete mathematics. Okay. Well, we have about 5 minutes left, so I don't think I'm going to move on to chapter 4. I'm going to spend maybe a few minutes to go over one of the bonus questions we did before, because I've never talked about that question. Because that question, the reason I want to talk about it here is because it also uses indirect proof, sort of like the indirect proof idea. So maybe we can help you. It was chapter 1 again. Okay, so if you remember this bonus question, we did it before. So two natives A and B address you as follows. A says, both of us, did I switch? Both of us are knights. B says, A is a knave. Okay. So there are only two kinds of people. One type of person always lies. The other type always tells the truth. So we want to determine what are they. Okay, so what we do is you can use indirect proof to do that. So for example, there's nothing for us to prove, but you can try to say, I'm going to determine what A is. Let's say, I don't know what A is, but there are only two possibilities for A. A is either a knight or a knave. The same thing for B is either a knight or a knave. I just need to determine one of them. So what we do is, it's kind of like saying, okay, I'm going to suppose A is a knight. I don't know whether A is a knight or not. If this gives me a contradiction, what does that mean? If this assumption gives us a contradiction, it means A cannot be a knight, right? Then A has to be a knave. Okay. But if you say, can I start with suppose A is a knave? If you want, you can. If it does not give you contradiction, then that means A is a knave. If it does give you contradiction, that means A cannot be a knave. All right. So if I assume A is a knight, go back to look at what A says. A says both of us are knights. If A is a knight, that means A always tells truth, right? So A tells truth, always. And what he said will be true. What did he say? He said both of us are knights, which means B is what? From what A says, B is what?
Knight.
B is what? Is a knight, yes. Because whatever A says is always true, because we assume A is a knight. If A is a knight, whatever he says is always true. And he says both of us are knights, so which means B has to be a knight. So that conclusion follows from what he says and follows from the assumption and the definition of a knight. So if B is a knight, look at what B says. B says A is a knave. Because B is, from our conclusion, B is a knight, which means B always tells truth. Whatever he says should be true. But what did he say? He said A is a knave. So because since we're saying, since B is a knight, what he said it should be true. He said A is a knave. So this should also be true. But there's a contradiction here. Then A is a knave. What is the contradiction? Can you see what the contradiction is here? That's right. We assume A is a knight. We end up with A is a knave. That's a contradiction. Right? Okay. Based on, how did I get this? This is our assumption. Suppose A is a knight. This comes from what A says. Because they said, A says both of us are knights. So that's why you get this conclusion, based on what A says. How did I get this sentence? Based on what B says, and also that conclusion. So there's a contradiction here. You can say a contradiction. And whenever you get a contradiction, it tells you what? Your assumption is false, right? This cannot be true. That means A cannot be a knight. A cannot be a knight. It's false, which means A has to be a knave. A is a knave, right? So, and then if you know A is a knave, it's easy to tell. So A is a knave, so A is a knave. And if A is a knave, what is B? A is a knave. He always lies, right? He said both of us are knights, which cannot be true, which means what? B is, I guess like, yeah, I don't have time to finish this, and I have to probably finish this next time. Okay. So both of us are knights. That is not true because he lies, which means
Your meeting has ended.